before we get into it, just a couple things on second order differential equations. This is the main form that all of them follow. It's going to be some px y double prime, qx y prime, rx y, and some function x. And so what it means for it to be homogeneous is that all of these functions of x on the left-hand side need to be constants. So it's a, b, c. It's a homogeneous constant coefficient second order differential equation. And so these are going to have a solution, y of x, that equals a solution, a complementary solution, y c of x. I'll dive much deeper into this when we go over it. And then we have a non-homogeneous equation. Same constant coefficients on the left-hand side, but now on the right-hand side we have a non-zero function of x. And so when we're solving these, the solution is composed of this yc of x and a particular solution, yp of x. And so essentially when we have something like this, we're solving homogeneous first, and then we're doing some special math afterwards to get the particular solution. But yeah, let's dive into it, starting with homogeneous constant coefficient equations. So like I just said, we have a general form, a y double prime, dy prime, cy equals 0. So when we're confronted with this, the first thing is that we know that there's a solution that exists of this form. This is a proof I'm not going to do, but you can trust me that a solution like this exists for these equations. So this r is what we want to solve for, and we can solve for r pretty easily by creating something what is called the characteristic polynomial. So r equals a r squared plus br plus c, with these coefficients coming from what's in our problem. So after we solve this for r, we have a few different possibilities. This is just like any standard quadratic equation. So we have like three possibilities. We have two real and distinct roots. So r1 does not equal r2, and they're both real. Then we have one real root. So we have r1 equals r2. And then finally we have complex roots, where r1 and r2 are in the form of some lambda plus or minus mu of I. These are our three cases, and the approach to this problem is pretty much the same every single time. Immediately figure out the characteristic polynomial, figure out which case it's in, and then we have a specific solution for each. So let's get into this first one right here. Real roots. Real distinct roots. So when we have two real distinct roots, we know that the equation is going to take this form. Where r1 and r2 is what we just solved for in that characteristic polynomial, right? So in this first case, this is your answer. That's pretty much it. And on the exam, that should be the first thing you're solving for every single time. So let's walk through a little problem just to see what we have here. So let's see this equation, y double prime plus 11y prime plus 24y equals 0. This is the form we're looking for. We don't have to do any further like simplification or anything. We can just go right into solving for that characteristic polynomial. R equals r squared plus 11r plus 24 equals 0. This factors down to 8 and 3, which gives us our r1 and our r2. It doesn't matter which one you put as r1 or r2, you'll get the same solution. So now that we have r1, r2, like I said, we're plugging it straight into this solution that we have. So we have c1 e to the negative 8x plus c2 e to the negative 3x. That's our general solution. Now, if it's an initial value problem, there's one more thing that you guys haven't done on the, or weren't doing on the last exam. And if we have some initial condition, y of 0 equals 0, then we're also going to have an initial condition y prime 0. So now when we're trying to solve the initial value problem, what we're doing is we're not only taking this equation that we just found, but we're also going to differentiate it to get y prime of x. And so you can see that in this case it's negative 8 c1 e to the negative 8x minus 3 c2 e to the negative 3x. We have these two equations. We plug in the initial values. So here we have y0 equals 0. It's pretty nice. Pretty much just simplifies to c1 plus c2. And then we plug in our y prime of 0 equals negative 7 here. Oops. And this is pretty straightforward as well. We have our negative 8 c1 minus 3 c2. So we just have a system of equations now. We're solving for it. We're getting our c1 and our c2. I'm just going to go ahead, tell you guys the answers. It's c1 is 7/5. C2 is negative 7/5. So with these two, we now have our specific solution, which we can write out here. It's negative 7/5 e negative 8x, and then I think it's the first. Minus 7/5 e to the negative 3x. That's our solution. That's should be like second nature because everything builds on this. So this is your real distinct root case. But now we're going to go into the other two cases, which we'll see here. So now what if we solve that characteristic polynomial and we have one root, so a repeated root. If this is the case, we have a very slight modification to our solution. If y of x equals c1 e to the rx, and then we have our second term is multiplied by an x. There's our solution form. Let's try it real quick. We have y double prime minus 4 y prime plus 4 y equals 0. So this should be like your instinct on this exam. Immediately plug it in to this equation. We have r squared minus 4r plus 4. This comes out to r plus 2 all squared, meaning r is 2. We have r, plug it in and get our solution.
Excuse me?
Yeah.
Doesn't R equal -2?
Yeah, you're so right. Yeah, so C1 e to the -2x. Oh, wait, sorry.
Oh.
Yeah, sorry. It's my fault. Yeah, so, and we just plug right into the solution. C1 e to the 2x plus C2 x e to the 2x. There's our solution. And then finally, what if these roots are complex? Yet another like easy solution which you should be going for. So we have y of x equals C1 e to the lambda x cosine of mu of x plus sine of mu of x. And so, just gonna rewrite that real quick. So what we have is C1 e to the mu lambda x cosine mu x plus C2 e to the lambda x sine of mu times x. So, exactly like before, when we have a homogeneous differential equation, second order, we can just plug it in to that characteristic polynomial, solve for r. In this case, we need to use the formula to solve for this. We have 8 plus or minus square root 64 minus 68 all over 2. This comes out to be 4 plus or minus I. Now that we have R, now that we have R, we plug it straight into this equation up here. So, this is supposed to represent that lambda plus or minus mu of I. In this case, mu is just 1. So we write out our general solution. And that's it. That's your, that's the homogeneous constant coefficient equations. This is like the foundation of this exam. So everything we're doing next is gonna be based on this. So it really pays off just to immediately gun for the solution. But yeah, that's pretty much it. So we're gonna move straight into non-homogeneous constant coefficient equations and the 2 ways to solve them. So when we have a non-homogeneous equation, like I said before, that just means that on the right-hand side, we no longer have 0, we have a function of x. So we have ay double prime plus by prime plus cy equals some g of x. And so now, when we're confronted with this, what we have to do is find the solution, which will take the form of yc of x plus yp of x. And so this yc of x comes from the solution as if this was homogeneous. We basically take this equation, drop g of x, and solve for it exactly like we were doing before. The tricky part is this capital Y p of x. And to solve for this, we're going to have to use either undetermined coefficients or variation of parameters. So let's start with undetermined coefficients. This method is essentially just algebra. It's a lot of it, but it's not too integral heavy. So the way it works is that we have some g of x here, right? And essentially what we're going to do is take a guess for our particular solution by just trying to replicate the form, right? So if our g of x, I'm going to write a little table out here. Our g of x is some ae to the beta x. We're going to guess that the particular solution is in the form of ae to the beta x. If we have a cosine beta x, we're going to guess a cosine beta x plus b sine beta x. If it's a sine beta x, we're going to guess the same thing. And then finally, if it's a cosine beta x plus b sine beta x, we're also going to guess the same thing. The last case is if we have some nth degree polynomial. And in this case, we kind of replicate it with some coefficients. So writing it out formally, we have a n x to the n plus a n minus 1 x to the n minus 1 plus dot 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 a1 x plus a naught. But what this really means is if we just have an equation that's just x squared minus 4x plus 1, our guess is in the form of a x squared plus bx plus c. And then something to note actually is that if one of these coefficients is missing, let's say the equation was instead x plus 1, we have the same guess for our particular solution. So that's something to watch out for, because if you're not including one of these terms, you're going to come up with a completely different answer. So let's walk through a little problem. We have y double prime minus 4y prime minus 12y equals 3e to the 5x. So, like I said, the first thing you should be doing is using your characteristic equation, polynomial, to solve for yc of x. So, we rewrite this as a homogeneous equation. We get r and we find our complementary solution, yc of x. that's your first part. Now, we're going to consider this g of x. Looking at our table, what does it look like? It looks like the first term in the table, a e to the beta x. So our guess is going to be a e to the 5x. So now that we have our guess, we're going to plug it in as if it was y in this equation. So we're just saying our particular solution y p of x is a e to the 5x. So if we're going to plug it in, we need the first and second derivatives. Yp prime of x, this is 5 a e to the 5x, and yp double prime x, and this is 25 a e to the 5x. And so what we do, we plug it back into the equation. And we set it equal to our original g of x. And so what we have here is just algebra, 20 minus 20, or 25 minus 20 minus 12. We get negative 7 a e to the 5x equals 3 e to the 5x. This means is a is negative 3 over 7. Now that we have a, we can get our particular solution. So I'll write it down right here. We have our complementary and our particular solution. What we do, just add them together and we have our general solution. There we have it. That's how we use undetermined coefficients. But there are a lot of caveats that we have to kind of go over first. So, first thing to consider is, what if our g of x isn't exactly like one of the terms we had on the table? What if it's a combination of two of those terms? So, what if our g of x is something like a x e to the beta x? Doesn't really fit in with the table because it's not a polynomial, it's not just an exponential function. So, what if our g of x is something like a e to the beta x, and then sine beta x? So, if it's a product of two forms that we know and we can use variation of parameters on, we take the product of their guesses. So let's do this first one here. Let's say we have something like this. Actually, let's do this one. Let's say we have something like our g of x is 16 e to the 7x sine of 10x. Well, we know our guess for the exponential. Let's call it a e to the 7x. And we know our guess for sine of 10x. So we write them out, and I'm just putting b and c here just so they're all different. But we write it out and we multiply it. And when we take this product, when these coefficients are multiplied, they just kind of absorb and make a new like unknown variable. So what we have here is the product, right? We multiply A times B, it just becomes A. We still don't know the value. We multiply A times C, it just becomes B. That's our guess, and if we were to have a solution with this or a problem with this, this is what you would have to differentiate twice and plug in to find the values for A and B. Yeah.
So what about the left equation over there?
Yeah, I'm going to do an example of that right now. So let's say we have something similar, a polynomial times an exponential function. Right? In this case, our guess for the polynomial is a polynomial with all terms written out. So this one, just because it doesn't include that last term, doesn't mean you can't include it here. That's essential. And then we have a guess for our exponential function, right? So when we multiply all of these together, we have something that looks like this. And then that's what you're going to be differentiating and plugging back in. So this also extends if we have three terms. So what if it's a combination of like three forms? We have three functions, same exact thing. Take a guess for each one of them. And we distribute the products. So in this case, what we get is, we can think of almost doing this step first. We have e to the 2x, ax plus b, times the same from here. And now we can think of distributing this into each one of these terms. And so what we get is e to the 2x ax plus b cosine 9 of x, 9x, plus e to the 2x cx plus d sine 9x.
So you can do it with as many.
Yeah. So this could keep going, and you could have like 15 guesses, but in the end, it's just algebra. You're merging these coefficients, so there's no such thing as like if we're doing these together, we wouldn't say this is abx plus ac, because those in terms are just coefficients we don't know. So we just rename them ab. Same thing that was going on here when we distributed into the cosine and sine terms. They essentially became new variables, so we renamed a and b, c and d.
Wait, so two questions. One, where did c go from the second to last line? Shouldn't it be cd instead of de?
From here to here.
Yeah.
So I'm saying I'm just renaming this. So instead of going AB, and then it's ABX plus AC.
Yeah.
Instead of having that notation, we know that A is some number, and then B is some number, right?
Right.
So we know their product is also some number, so I'm just renaming it back to A.
Yeah, that's fine, but I'm saying, like, there's no C in, well, I mean, I guess it really doesn't matter, they're just coefficients. Because there's no C on the line right above that? There's
Yeah,
no-
they're, oh, okay. Oh, I see. Yeah, no, it doesn't matter, yeah. It's just like a naming convention. So yeah, I could have totally had this as C. This is D.
And then, how did you get the second function in there after the a2x? How did you know it was that one?
This one right here?
This is a multi-polynomial, nth
Yeah,
polynomial?
this is the nth degree polynomial. So we have this x term here. It's just written backwards,
Yeah.
but it's of the form where we have a function of x, no cosines, no exponential terms.
For the n, so for the polynomial one, it doesn't need to be it doesn't need to be binomial. It can be anything.
Yeah, it can be like x cubed or something like that.
Yeah.
And then your guess for x cubed would be ax cubed plus bx squared plus cx plus d.
And you can have bx squared and cx squared in there and d because it all equals 0.
Yeah, these you will be solving for these or all of these coefficients with this method.
Okay.
So it's important to make sure, even if like technically it's 0x squared plus 0x plus 0, you need to make sure to include all these coefficients or else your math is going to be wrong.
Okay. Thank you.
So now let's think of the other case. What if it's just a product of two of these forms, or a sum of two of these forms? So what if it's something like this? So for this case, we really just add them together. It's so like if we had e to the 7x plus 6, right? We know that the guess for this one, a to the 7x, the guess for this one, since this is technically still like an nth degree polynomial, it's just x to the 0. We just guess one term, b, and then we put them together. So our guess for the particular solution is a e to the 7x plus b. So one more example. Our g of x is 10 e to the negative x minus 5 x e to the negative 8x plus 2 e to the negative 8x. So our guess for this one, a e to the negative x. Our guess for this term, this is a product. So we have an x here, first degree polynomial, b of x plus c. As for the exponential, we just have some d e to the negative 8x. And then finally, our last term here, let's call it e to the negative 8x. And so, first of all, just to simplify, I'm going to distribute this d here, and just like last time, it basically just disappears. We can rename this to d. It doesn't matter what these names are. You can be consistent, you can change them. It won't affect your final answer. But then, one thing to note here is that you have to be careful to make sure you're getting rid of all of your like terms. So if we were to actually distribute this, we would have bx e to the negative 8x plus c e to the negative 8x. But if I bring this down as well, our other term can be added together, right? So in this case, instead of doing extra math with this term right here, we can just completely drop it. Our solution for this, our guess, can completely eliminate this d term because it gets absorbed with this term right here. So it's important to just distribute all of these, because if you stopped right here, you would be solving for 4 variables. But if you took this extra step, you're now solving for 3. So it helps a lot. So let's do another example. So let's see. Y double prime minus 4y prime minus 12y equals x e to the 4x. So this is actually the same one as that one, just a different g of x. So we know our complementary solution is going to follow that form. So now we have to figure out a guess for our particular solution. So g of x, x e to the 4x. So that's a product of 2 functions of x. We have a polynomial and an exponential. So we can write it out. We can simplify it. And now, just like last time, we have to take the derivatives of this in order to plug it back into our original equation. So, first derivative is e to the 4x, 4ax, plus 4b plus a. And then our second derivative is e to the 4x, 16ax plus 16b plus 8a. So let's plug it in. Let's solve for these a, b, and just a and b. Let's find our solution. So we're plugging it in for y prime, nothing to be done there. E to the 4x, e to the 4x, 16ax plus 16b plus a minus 4 times e to the 4x, 4ax, 4b plus a minus 12 ax plus b e to the 4x equals our g of x from the start. So this is just e to the x. never mind. I was looking at the wrong one. All right, so if you do some algebra or get something like this,
Why did you take the second derivative of yp of x?
because we plugged it in for y double prime up here.
Okay.
So that's this term right here.
Oh, you're plugging it back into
Yeah, plugging it back into the original equation. So this is all just simplification. It's really annoying. It's really important to have no simple mistakes, because in the end we'll have something of this form, right, where it's simplified. And so here we need to find these coefficients, but it's easy to see that this term right here, this needs to equal 0. Because there's no term on this side that has the factor e to the 4x. We have x e to the 4x, which kind of matches here, but nothing on this side that's just e to the 4x. So what does that mean? It means that 4a minus 12b equals 0. And so in the same fashion, this term needs to equal x e to the 4x. So we have negative 12a equals 1, because our coefficient on this side is just 1. So we have two equations. We go ahead and solve. We find a, we plug in a, we find b. And we have our particular solution. So combine that with our complementary solution that was found at the start. That's our answer.
Can you say that again, why they equal 1 and 0?
Yeah, of course. So I'm just writing it out here so it's easier to see. So the reason is that we have these coefficients here, right? This is our function of a and b multiplied by our function of x, right? So we know that these two sides need to equal. So when we're solving for a and b, we know that there is no term on the right-hand side that looks like this, which essentially means that if there was, it would be multiplied by 0. So this term needs to be like this one, and this term needs to be like this one. And how are we going to do that? We're going to do that by solving for a and b that makes this true. So if I was to actually plug in the answers I found, I would get the same term here, and then likewise for the other one. we're just trying to make these sides look alike. And in a lot of cases, that's going to be kind of easy to see. Like maybe if there's just ax and the other side equals x, we can deduce that a must equal 1. But if it's something like a squared plus b, and on the right side it's just x squared, we know that there's no term on that side that doesn't have a factor of x squared. So we know that this b can just equal 0, and this is the only term that we're really concerned about. And here, in this case, a equals 1, because there's just a coefficient of 1 in front of the x squared term.
Thank you.
Excuse me.
Yeah.
So, at the end of this equation with the yp of x, you said to combine it back into the original equation?
Yeah, so we're taking this complementary one, we're taking the particular solution, and we are just adding it. That's it. That's all you have to do.
Okay. You don't need to
I
simplify
can write it down.
Wait, okay.
So our solution would be then plus yp of x, just writing it out here, plus this one here. Just So this is your general solution. And so now if it was an initial value problem and you got your like conditions at the start, this is when you would start solving for them once you arrive here.
Okay, thank you.
All right, one last example. So, I want to do this example because I want to show you like a certain situation that might come up. So, let's say we have y double prime minus 4y prime minus 12y e to the 6x. So, if you just look at this and take a guess for the particular solution, your guess would be a e to the 6x. But if you went through all the trouble of differentiating this and then plugging it back in, and you did the algebra, you would get 0 equals 6x. And that makes no sense. So what you have to realize in this situation is that if we were to actually solve this equation, this is the same exact one as previously. Our complementary solution is that. What we have to realize is that our guess looks exactly like one of the terms from our complementary solution. And if that's the case, you're going to get like a weird result just like that when you try solving. So what do? We have to just modify it slightly. Instead of a e to the 6x, we do a x e to the 6x. So that's our guess for the particular solution, and now we can go through the same process.
x come from?
We're adding it to make this work. So you essentially just have this original guess. It's not going to work because it looks exactly like one of the terms in your equation. You multiply your guess by x. That's it. There's like a complicated proof behind why it works, but
That's fine. But
that's
what about the other equation? Do you need to multiply x there too?
which other equation?
The yc of x?
No, this stays exactly the same.
Okay.
It's only the particular solution you're concerned with. If we plug this in, more algebra here. This simplifies down. I'm not going to bore you with that, but it just simplifies down, and we get a new solution here that actually makes sense. 8a e to the 6x equals 6x. 8a must equal 1. So we know a equals 1 over 8. So now that we know a, we can tag it on to our, just get our actual solution by adding our complementary to our particular. And there you go. It's going to be how you're solving something like that. So like I said, that's it for undetermined and coefficients, but it's just very annoying, so try not to make any mistakes because that might cost you when you're solving for A, B, and C. Yeah, any questions on this? All right. So now we're going to do variation of parameters. So variation of parameters. So this is just a different way to calculate your particular solution, yp of x, and it differs in a few ways. First of all, it's more general. So we're not like restricted to those forms that we had before. And we like didn't have guesses for some functions, right? We could like take the product in some, but there's some functions that don't work. So this one's more general. There's also the fact that you must have yc of x to use variation of parameters. So in undetermined coefficients, it's not required, but for variation of parameters, it absolutely is. So we have our non-homogeneous equation. We solve for yc of x, where we have two solutions, right? y1, y2. And there is just one equation to find the particular solution, but it is very annoying. So you might have seen it in other ways. Some people like split it up a little bit differently. Personally, I just write it out all at the same time, just to keep track of it all. So, what is W? W is something called the Wronskian. It is a special determinant. So what that means is we have these two functions, f and g, and then the Wronskian is the determinant of those two functions and their derivatives. And there's a very simple formula for this. When we have a determinant a, b, c, d, you multiply the diagonals and subtract them. So we have a times d minus b times c. So in the case of the Wronskian for two functions, f and g, we have f times g prime plus g times f prime. So this is what we need to know for variation of parameters. It is a bit complicated, especially when the integrals get difficult, but yeah, let's try some examples.
Excuse me?
Yeah.
For the rocks, what's it?
The Wronskian, yeah.
Is that supposed to be plus GF prime?
Oh, so sorry.
Thank you.
So let's apply this on some function. All right, so we have our non-homogeneous equation. We have some g of x. Like I was saying before, your instinct should be to immediately solve for that characteristic equation. So what do we have? We have r equals r squared minus 2r plus 1. What does this give us? It gives us r minus 1 squared. So we know that r equals 1. So our complementary solution in this case, we have c1 e to the x plus c2 x e to the x. That's our complementary solution. So this is our first function of y. This is our second function of y. And what we can do here is start calculating the variation of parameters based off of what we have. So first thing to do, let's calculate the Wronskian of y1 and y2. What do we have here? We have e to the x and x e to the x. So derivative of e to the x, just e to the x. Derivative of x e to the x is e to the x plus x e to the x. When we evaluate this, we get something like this. And so this comes out to e to the 2x. This, when you distribute it, this term cancels out with this term. So now let's write out the formula based on what we have. So we have negative y1 integral of y2 times our original g of x and over the Wronski. Plus now y2 times the integral of y1 times g of x times the Wronski. So that's the solution for the that's the particular solution. We need to evaluate it. It gets a bit rough, so hang in there. First thing to do, simplify it down. Yeah.
For the Roxian, it's e to the 2x, right?
Yeah.
Why are you multiplying e to 2x times x?
This is coming from our g of x right here. So in the
that's g of also the g of x
Yeah.
would be e to the x over x squared plus 1. So just
yeah,
multiply.
I just shortened it just
Yeah.
for a little shortening, but that's effectively the same. So let's solve it real quick. So this actually cancels out. These e's all cancel out, and we're left with x over x squared plus 1. And on the other side, we have 1 over x squared plus 1 dx. These are not like friendly integrals. You probably will get easier ones on the exam. But this one right here, this is the inverse tan tangent. That's just like a integral you should memorize. Over here, a little more complicated. We're gonna do a u sub. Let's have u equal x squared minus 1. So du dx equals 2x. So dx equals 1 over 2x du. So let's plug that back in. Just focus on the integral. We have 1/2. We're taking it out. 1 over u. du. What does this equal? This is an integral we're familiar with, right? 1/2 natural log of u. So now that we have both of these integrals evaluated, we can put it all together in one go. We have negative e to the x times 1/2 ln of x squared plus 1. And then we have our other term, x e to the x times the inverse tangent of x. Yes.
For your u equals x squared minus 1.
Oh, yeah, sorry. So that's the method. It's sometimes gets a little tricky, but this is indeed the answer. So last step, don't forget this step. You put it all together to get your solution. Your complementary solution. Added to your particular solution.
You don't need C anywhere?
C is right here.
I'm sorry, for the intervals.
Oh, yeah, no.
No?
You know why we don't need C for the intervals? Isn't that just like a C1 and C2 like made up for it? Or something?
Yeah, maybe. Like I said, I'm not here to like give you guys proofs.
Yeah.
Just how to do it. So when the test comes, you know what's going on.
Can you go back to the board after this?
Yeah, of course. All right, that's yeah.
I'm sorry. So the Ronchian is the only thing in the denominator over here. I'm a little confused as how x squared plus
Yep.
1.
Let me write it down.
Oh, it's because
Oh, wait, I'm
your
sorry.
g of x
G of x is a factor.
All right. Yeah. Good. All right. Any other questions? All right. We're gonna go back to variation of parameters because we're gonna need to use it later. But for now, let's go on to Cauchy-Euler equations. So what we have here is we're looking for a new form of second order differential equation. We no longer have constant coefficients. What we have is something that looks like this. A x squared y double prime plus bx y prime plus cy equals g of x. And so exactly like the last time we had our characteristic polynomial for homogeneous and non-homogeneous, but it was kind of the same. We have a new characteristic equation, and it looks like this. And now when we solve for r, and we have a r1, r2, we get our complementary solution, and it looks like this. But just like last time, we have three cases. So real, distinct roots. We have a R1 that does not equal R2. So this is the same form I just wrote down. C1 x to the R1 plus C2 x to the R2. Next case is a repeated group. R1 equals R2. And we have another form. Just like last time, we tagged on an X to our second term. This time we're tagging on a ln of X. So you can just simplify this by writing C1 plus C2 ln of X all times X to the R. And then finally, if we have complex roots, we have R in the form of lambda plus or minus mu times I. We have a new form that looks like this. So, 3 cases. Let's do some practice. It's essentially the same as your homogeneous case with constant coefficients, just 3 new variations to memorize. I'll keep this up for a couple seconds. Yeah.
Lambda over here, is that just going to become like a constant?
Yeah, lambda and mu are constant. So like, if it was like 3 plus 4i, lambda is 3, mu is 4. Let's do a quick example of a homogeneous case where x equals, g of x equals 0. So when you see this, first thing you should recognize is derivatives of y have a function of x attached to them. So you know it's the Cauchy-Euler equation. So knowing that, first thing to do, characteristic polynomial. So we solve the polynomial, we get that we have the repeated root case. So what does that mean? We plug it straight into that equation we wrote down. What about if we have something like this? X squared, y prime, plus minus xy prime, plus 5 equals 0. Same exact thing. We start by plugging into that characteristic polynomial. We get something that looks like this. We have to use the formula for it, but we get our answer that r is equal to 1 plus or minus 2i. So 1 is your lambda, 2 is your mu. You plug it right into that equation, and you find your solution. relatively straightforward. Plug in the characteristic equation, plug it into whatever solution fits the roots. Let's do one more example, this time non-homogeneous. We have x squared y double prime minus xy prime minus 3y equals 2x cubed. So, just like before, we start by solving this as if it was homogeneous, right? And the way we do that with this new characteristic polynomial. So we get our two. Roots, -1 and 3. And knowing that, we get our complementary solution. They're both real, they're both distinct, we plug it into this equation. Now we can focus on this g of x, and let's try variation of parameters again. It's really important to note, though, variation of parameters, you need a specific setup. When you have a equation like this, to use variation of parameters, you need a to equal 1. So in this case, there's an x squared multiplied by y double prime. So before we go to solve it with variation of parameters, we need to rewrite that equation. We can just divide all the terms by x squared, make y double prime have a coefficient of 1, and then we can use variation of parameters. So if we divide by x squared, we get y double prime 1 over x y prime minus 3 over x squared y equals 2x. So this is the equation we'll be using to solve for variation of parameters. Or sorry, this is the g of x we'll be using when we try and solve variation of parameters.
Why didn't you, couldn't you have just used undetermined coefficients?
Yeah, it also would have worked.
It's just preference?
Just preference. I just wanted to get another example of variation of parameters.
Okay, and also, why didn't you just multiply x to the g of x instead of dividing by x squared?
One more time, sorry.
You said earlier that you could just multiply 2x cubed on the
Yeah.
original equation. Because one of the roots is x cubed, it wouldn't work out if you just kept it like that. So you said you could multiply x to the the g of x equation, correct?
Oh, that's only really in a non-homogeneous, not a Cauchy-Euler equation. Since we're doing Cauchy-Euler equations, it's a bit different.
Okay.
Also, yeah, so you're right. X cubed is like a part of the complementary solution, So if we were to do undetermined coefficients, your guess would need to be one order higher, so like ax to the fourth, basically. But so yeah, if we were doing undetermined coefficients, our guess based on this, we would start with ax cubed, b x squared, c x plus d. But you're right, this matches that form. So we multiply this whole thing by x. So this was the same case as when we had like a complementary solution. That was like c1 e to the negative 2x plus c2 e to the 6x. And our g of x was e to the 6x. And remember, in this case, we have that weird quirk where if we tried to solve it with undetermined coefficients and left g of x normal, even though it matched one of these terms in the complementary solution, we could not find the guess for a. So what we had to do is multiply this by x. So that was our guess. So this is very similar. But that's for undetermined coefficients. We're going to solve this one with variation of parameters.
Are there any times you have to use variation of parameters?
Yeah, so sometimes you might not know your complementary solution.
What type of question would that be? Like, what would they give you?
Nothing on this exam.
Nothing
So,
else to say.
Yeah. If you're curious, yeah, something interesting to look up, but you don't have to worry about it for this exam.
So you can always use this exam undetermined coefficients problems.
Yeah, so what they'll actually do is they'll ask you
To use
to
variation.
use a specific one, so they won't make you guess. Alright, so let me rewrite that equation. So we have a new g of x, but we already have our complementary solution. So we know our y1 and our y2. So we start by calculating the Wronskian. Here we have negative x to the negative second power. Here we have 3x squared. We take the determinant of this, multiply the diagonals, and subtract them. This comes out to be 3x plus x, or 4x. So I'm just going to rewrite that underneath. Now that we have our Wronskian, we can plug this right into that equation for variation of parameters. Our particular equation will be negative y1 times the integral of y2 times g of x all over the Wronskian plus y2 times the integral of y1 times g of x all over the Wronskian, and these integrals are way easier than the ones we had before. So simplifying a little bit, we get something that looks like this. I heard somebody asked where 4x came from. Are you like referring to right here? I don't know who asked that. Yeah. There's a specific equation for determinants. So when you have something like this, I'll write it on the side. So we know the Wronskian, two functions. Looks like that, with these bars meaning a determinant. And so when we have something like this, there's a very simple formula to calculate it. We multiply the diagonals, a times d, and then subtract the other diagonals, b times c. So what we did right there is exactly that. We multiply the diagonals here. Well, I'm missing a 3, sorry. Is that why you were confused?
That's probably why I was confused,
Yeah.
but I see it now, yeah.
Yeah, diagonals minus other diagonals, and we get 4x.
Just to confirm, so undetermined coefficients is when you find like the derivatives of like the y,
And then you plug them back
plug
in.
it back in, and various parameters is this equation.
Yes.
Solve for
Yeah,
whatever we're solving for. So are we solving for x?
we're solving for the particular solution, yes.
Oh yeah, just whatever.
Yes.
Okay.
So let's wrap this up. Integral x cubed is going to come out to 4/4. Integral of 1/x comes out to L of x. So there we have our particular solution. And to get our final solution, we add everything together. Our complementary solution from before. And our particular solution that we just had. So there we have the method of variation of parameters for Cauchy-Euler equations. This is something like you might see on your exam, and specifically, I think the hardest part is just remembering that before we start variation of parameters, y needs to have a coefficient of 1. Yeah.
Is that the only restraint for variation of parameters?
Yeah, pretty much.
You have to come up with your last C before you factor out.
Yeah, because if you did this first, this would no longer be in the form for Cauchy-Euler, right? The form is x squared x, and then just like some coefficients. So, I mean, technically it works, but just to be like safe before you start going on with variation of parameters, you should figure out your complementary solution using the methods we like wrote down before, and then work on the particular solution. All right, so we're gonna move on. Does anybody have any questions?
I did see something that the professor said that mass spring systems weren't going to test. Like,
Weren't gonna be on the test?
I could be wrong about that, but I think I saw.
Can anybody else confirm?
I don't think we've ever seen mass spring, at least in our lecture.
Yeah, we emailed the professor. He did say Mass Springs was on this. So, Or at least one of the professors
Professor
might have
Professor
it.
Romney.
Yeah, Robbie didn't mention it here.
I don't know.
I also have a syllabus. Who's your teacher for?
I don't know his name.
Alright.
He's I think he's like Kowalski, something like that.
Oh, I'm just checking the syllabus I have. Yeah, so on this syllabus it does say it's on it. That might not be for every teacher, so at this point, I'm still gonna do it, but that's up to like you to decide if your teacher is putting this on your exam. So mass spring systems are essentially like the application of everything we've been doing so far. Essentially just a word problem that you have to figure out. So this is your setup. So I'm just gonna draw out what we're actually modeling here. So first of all, we have a spring. It has a natural length of L, so without any mass on it, it hangs down, and it has a length of L. But we're attaching a mass to it. So not only does it hang down at a length of L, but then the mass brings it down further with that length being capital L. So when this is completely at rest, we call this the equilibrium point, and we mark this position as x equals 0, displacement equals 0.
Is L the full length of the thing or just the?
Just the extended section.
Okay.
So
At small
small l is the natural length of the string.
L, is that
Or,
what x equals 0 that this goes to?
X equals 0 at L plus capital L.
Okay.
And then one last thing to note is that we're modeling the movement of this spring, but specifically what we're doing is, how we're modeling it is that the downward direction is positive. So if a problem says it's moving with a velocity of like 2 feet a second, that means it's traveling down 2 feet a second. If it says negative 2 feet a second, it's traveling up 2 feet a second. So have we modeled something like this? Well, I mean, I'm not a physics major, but there are a couple forces that act on this system. Gravity. Force of gravity, that's mass of the spring times gravity. The spring has its own force pulling. And it looks like this. K is a constant in this case, the spring constant. We have a dampening force. Where we have another constant, or another coefficient gamma here. And then finally, external forces. Just some f of t. And this is essentially our g of x that we were working with before. So everything in this section is taking every single concept we've just been covering and applying it in a word problem to a real world system. So we put these together and we have a differential equation for modeling it. Mx double prime plus gamma x prime plus k x equals f of t, your external forces. So keep in mind x is displacement, so now we're not working with like y of x, we're working with x of t, right? And if you like remember from physics, you have your displacement, you take the derivative, you have your velocity, and so on. So this is our fundamental starting point. This is what we're going to try to like work out, essentially, with the information that's given to us in the problem. And then we're also going to get some initial conditions. So we're probably going to get something like x of a, and since that's your standard, let's call it x of e, you're going to get this one and its first derivative, and essentially this is your initial displacement. Sorry, this is 0. So initial displacement at time equals 0, and this is your initial velocity at time equals 0. And so with all these facts, probably just gonna get a blurb on the system, and you have to get this equation and use the same methods we've been doing before to solve it. So let's get right into it. There's a few different cases. So the first thing I want to talk about is a free, undampened vibration. So what does that mean? Free really just means there's no external forces. So we're back to the homogeneous case right here. And undampened means that that middle coefficient, that gamma, the gamma of x prime, that term is not in the equation.
What was the other term?
What? Sorry?
You said free, and then what was the other term?
Undampened.
Okay.
So like I said before, we're kind of essentially just dropping that middle term, and we're left with the following equation. So now there's just a couple things here we need to take care of. A couple formulas. So this is exactly what we did before. I mean, mass and K are pretty much guaranteed to be constants, so we can use the same methods we had with the homogeneous case. There's actually you can do it yourself, set up the characteristic equation, but shorthand, the solution is as follows, where this omega naught is square root of k over m. So that's your solution for it. And since this is complex, we have the following solution. And then there's one last component. This is where it gets a bit weird. So since we're modeling what is essentially just like displacement over time, what we can do is condense this into one term using phase shift. So we can actually rewrite this in a specific way. We have r cosine omega naught t minus delta, where r is defined like this from this original equation, and then we have our delta defined as the inverse tangent of C1 over C2. Sorry, C2 over C1. So when you get a problem like this, you'll start by getting here. And then if it asks for it, I'm not sure if the professor will ask for it on the exam, but it is in the textbook, so you'll simplify it down in this form. So we'll do an example of it. It gets kind of weird. Yeah, what's up?
For the r equals plus or minus omega naught t, is that the I? What does the I mean?
Imaginary. It's a complex number.
It's always complex.
It's always complex because k is always greater than 0.
So why is that always complex then?
Um,
It's always greater than zero.
Because yeah, if you just like do the math real quick and use the characteristic equation, you get mr squared plus k. So if I was to solve for r, it would be okay, this 0. It would be what, negative k over m squared. So these two numbers right here, k always greater than 0, mass hopefully greater than 0, and since we multiply by negative, then this is always negative.
So you just factored out the negative to the I.
Yeah, essentially we do this. Oops. Just like that.
Wait, where get that equation r equals square root of negative k, right?
Right here. Which equation, sorry?
The r equals negative. The r equals square root of negative k, right?
Oh yeah, I just
Is that the quadratic equation?
you can just do it like in smaller steps.
Oh, just solving for r.
Yeah. Just like that.
Okay.
Yeah, so let's do an example. For one of these. So I'm gonna write out what you'll see on this exam. We have a So you're gonna get something like this. I wrote it out in bullet points just to make it a little bit easier, but a 16-pound object stretches a spring 8/9 of a foot by itself. So remember, if we go back to the diagram, we have our capital L here is the displacement from its natural position. So that line is saying that adding the mass stretches it 8/9 of a foot. Then we have, there's no damping or external forces, so we know we're working with an equation like this where gamma is 0. Then we have, it is initially displaced 6 inches upwards. What does that tell us? X of 0 is negative 1/2. You have to be really careful with units here. 6 inches upwards, that's half a foot. And then it has an initial velocity of 1 foot downwards. 1 foot a second downwards. So that's our derivative of x at 0, and that's 1. It's positive 1 because, like I said before, down is your positive direction, right? So when the spring is moving downwards, we essentially treat it as if it was moving in a positive direction. So we have a couple things. First thing to note is that 16 pounds, that's not mass, that's weight. So we have to figure out our mass. So we have this equation, weight equals mass times gravity. We work it out to be mass equals weight over gravity. 16 pounds in imperial, gravity is 32 feet. And then, so this comes out to 1/2. So we now have our mass of 1/2. So now we use this equation right here. This is important to note down. If you go through the process of deriving that equation right there, you'll get 2 terms, these 2 terms, and when it's stationary they cancel out, so we don't include them in the end differential equation. But this is essentially saying the distance of mass and gravity is equal to the length that the mass pushes down the spring, this length right here. So again, you don't really need to know exactly why, but you need to know this equation because we're going to use it to solve for K. So mass times gravity, well, we kind of just did the same thing. It's just equal to your weight, and the length it stretches is 8/9. And this equals 18. So now we can write out our equation from before. So again, using the equation for omega naught, we get something like this. And this equals 6. So we know our equation is C1 cosine of 6t plus C2 sine of 6t. And then let's plug in our initial conditions, the IVP problem. So we get when t is 0, we get something like this. Just get C1 because it follows sine of 0 is 0, cosine of 0 is 1. So we just get C1. And then let's calculate our derivative here. when we plug this in now, what we get is our 1 equals prime naught, and we just get cosine here. So we get this is equal to 1/6. Here. So we now have a specific solution for our displacement. Let's write it down right here. We have our C1 negative 1/2 cosine 6t minus 1/6 sine of 6t. Yeah.
Do you know why specifically our x0 equals -1/2? Why those two are C1 and C2?
That's just how it works out, I guess. Yeah. So, last thing we're gonna do is figure out this phase shift. Now, like I said, not positive it's gonna be on the exam, but very good thing to know just in case. So, we have those two equations right up there, so we can figure this out. Delta of inverse tangent of these two. And obviously I'm not gonna make you guys calculate that. So that's what it is. So this is an angle in radians. And essentially this angle falls in quadrant 4, right? But the opposite quadrant would work as well for this phase shift. So what we need to do is consider two deltas. Delta 1, where we have our value we just found, and delta 2, which is delta 1 plus pi. Essentially just we have like an angle going out here, and we rotate it.
How do we know of the quadrants that the angle will be in?
So the unit circle in radians, we have 0 here, we have pi here, here we have pi/2. Yeah, hold on. And then 3 pi/2. So essentially, this number right here, actually we can also write it out like this to make it a little easier. We have 0, and then we have negative pi/2, negative pi, and negative 3 pi/2. So in this case, we take this angle, we realize that it's between negative pi/2 and 0, so it belongs in quadrant 4.
And so you would just want to rotate to the other side?
Yeah, so for the phase shift, it's just how it works that the opposite side will work as well. So knowing this, we have two deltas, but we need to figure out which one will work for us. And the way we do that is two more equations, which are these two. So what we do here is we plug in our delta 1 and delta 2, and we see which one holds true. So in this case, when you plug in delta 1 and delta 2, only with delta 2 will this hold with the C1 and C2 we found previously. So what does that mean? Our delta 2 is 2.81984. And our final phase shifted equation, x of t, is going to be our r times cosine 6t minus 2.81984. So that's the phase shifted simplified equation. Both of them are the same thing. It's modeling the same system. It's just an alternate way of writing it, and it might be easier to plot it or do other things with it.
Why is delta equal to delta 2 again?
Because if you plug in delta 1 and delta 2 into these two equations right
They are
here,
the same.
you'll get the results that we find here.
Oh.
So we found C1 and C2 before.
Yeah.
So when you plug in delta 1 and delta 2, it only holds true with delta 2. So in delta 1, I don't have the calculations on
So
it.
it's like whichever one
Whichever one it works with. yeah.
works like with C1
Yeah.
C2.
Yeah,
So
exactly.
if it works with C1, it would be delta equals delta 1.
Yeah, if you plug in delta 1 into both of these equations, and both of them are true for these C1 and C2 you found earlier, then yeah, you use delta 1. If you plug in delta 2 and it's right, then you use delta 2.
Going like all the way back to the beginning of the problem, how did you get x equals -1/2, x of 0 equals -1/2?
Yeah. So these are our initial conditions. This is included in the problem, and it will say that it is initially displaced somewhere. So here we have initial displacement 6 inches upward.
Oh, it's a
What does that
60.
mean? At time 0, at like initial time, we are displaced upwards in the negative direction, half a foot. Good?
Last question.
Yes.
So the definition for R is plus or minus, that's small omega?
Yeah.
I?
Yep.
I don't see any I on the board.
Oh. This goes back to the start, but if you're looking for a little bit of so yeah, you're totally right. In the start, like you said, like there's going to be a solution of this form, but when you plug in a complex number here, mu plus lambda plus mu I all times x, it just so happens to work out with this identity, Euler's identity, and it just so happens to work out that it just loses the I. So
Thank you.
yeah. So yeah, it looks something like this. And after you do the math and you combine it into your general form, it just cancels out.
Okay.
So you don't need it in the solution. So let's continue. So in that last example, we ignored the damping force. This time we're going to include it. But we're still not going to have any external forces.
So the last question was free and undamped?
Yes.
This one?
And this one is free and damped. So in this case, that coefficient is not going to be, or that coefficient gamma is not going to be 0. So when we write out the equation, we have to include it this time. And there's a little shorthand for the roots of the characteristic polynomial. It looks like this. This is just applying quadratic formula on the coefficients above. So in this case, again, we're solving it just like with the equations before. There's just one thing to think about. This gamma minus 4mk, the discriminant, which basically governs whether this equation is going to have real or complex roots. It has three cases, like I said before. We have critical damping. When this equation, gamma squared minus 4mk equals 0. So this happens when gamma equals 2 times the square root of m plus k. And this is our critical damping coefficient. That's just what this term is called right here. We also have overdamping. And this happens when gamma squared minus 4mk is greater than 0. And finally, underdamping. So, the last case. And this particular one, you're going to have one root. In this case, you're going to have two distinct roots. And in this case, you're going to have complex roots. So let's try a problem. Let's basically use the same spring from before, just this time we're going to attach a damping force to it. And so this damping force exerts 12 pounds when the velocity is 2 feet per second. So we have this governing equation. We found these constants before. Let's plug them in again. We had mass is 1/2. So we have 1/2 x double prime plus gamma x prime plus 18x equals 0. How do we find gamma? Well, this is the governing force for dampening. Right here, that just comes from how we model this scenario. Just another thing you need to remember. But in this specific case, we can just drop the negative. And so now we can solve with the information we got. I'm sorry, this is we can solve with the information we got. We have exerts 12 pounds when velocity is 12 feet a second. 12 pounds equals gamma times 2 feet a second. We see that gamma is 6. So now we can plug that back in. So you can go through this equation to find your roots, but there is another way to kind of go around, about that, and it's this critical dampening coefficient. So this always exists using this equation. So let's see what our critical damping coefficient is. So this is an equation that we know of, and essentially, when we calculate it, we get 6. What did we get for our system gamma? 6. That means we know we're in the critical damping case. If we were to calculate this critical damping coefficient and it was greater than 6, well, we know we're in a over damping environment. If it's under the critical damping coefficient, it's in an under damping system. So this happens at gamma greater than gamma critical damping, and then this happens at gamma less than gamma critical. So essentially, we just kind of got lucky here. It's not going to be necessarily the case, but it does tell us how many roots there are, which is very important. So in this case, we do get a final solution. We know there's one root, so it has the following equation. So this was the stuff we were going over in the homogeneous case, way at the beginning. So finally, we come to forced vibrations. So I'm going to continue writing on this board. Is everybody good with this? Yeah.
Why is this 6 negative again?
Well, we can work that out. So where's my page? Yeah, if you just work it out, R1, R2, it's going to be negative gamma plus or minus the coefficient. In this case, it's just 0, and then that's going to be over 2n. So what we have here is just negative gamma over 2 times 1/2 equals negative gamma. That's our R1, R2.
Oh, so you would have to do it again before your last step to find your action.
I think you should be plugging it into the quadratic formula anyway. This is just like a little bit of a shorthand way to get to the same place. But if you're given an equation like that, you should be calculating it the same way we have it. Any questions? So finally we have forced vibrations. So we're no longer in a free vibration. G of x does not equal 0. So some things to consider. This is when f of t does not equal 0, right? Some things to consider here is that this equation can take on a periodic form, one that contains cosine omega t or f naught sine omega t, or a combination of them. And when that is the case, there are like two special rules. First is if our resonant frequency that we solve for way up there, if that equals this omega, we have a case where basically this external force is the same as our resonant frequency. So it kind of amplifies it, it gets weird, and we can get a shorthand way to the particular solution. When it's not the case, we have a different particular solution. That is only if the external force is a periodic function. So if it was just like f of t equals t, then this doesn't apply, and we go through the same method of undetermined coefficients or variation of parameters. So these solutions, you can verify them with undetermined coefficients the same way, like if it was any of these, your specific guess for the particular solution would be like a sine wt plus b, or cosine plus b sine. But it's just a equation to get there faster. We can still figure it out in the same ways we did before.
Oh, why are those two equations the same?
That's a really good point. Yeah. So, again, if we have a periodic function, external force, we can use these two cases to kind of jump to the particular solution, but undetermined coefficients will work as well. So if you're unsure, or if you forget on the exam, you can just use the methods we were doing before to get to the same place.
So,
Yeah, first.
but force means that it's not free, and that means it's non-homogeneous?
Yeah. So force means this g of x is non-zero. So now after solving for the complementary solution, we also have to solve for the particular one. So I have one final example for you guys. And this time we have all forces considered. So we have 3 kilogram object attached to spring. Spring stretches 392 millimeters. There is damping. Damping force is 45 newtons. when the velocity is 50 centimeters per second. And there is a external force that has this form. F of t equals 10 cosine omega t. And then it goes, the system will experience resonance. So there's a lot to take in, but a few things to start with. This external force follows our periodic form, but it does not give us the omega in the cosine. But it does say the system will experience resonance, which means that we're in this case right now. This is the resonant frequency that we can find just from the spring itself, like we did before. So that means that the period of the periodic function is the same as the period of our spring system, and therefore the system will experience resonance.
Why is F not 10?
Sorry, what was that?
Why is F not 10?
No, that's just the external force.
Where do you get the external?
Oh, this is given. This is all given to you in the problem.
Where does it say? Oh, this is all given. Oh,
This is all
still
given.
the
Yeah.
Oh, okay.
So no work just yet. But let's start tackling this problem. The first thing to do is realize this is in kilograms, which is mass. So we don't have to solve for mass like we did last time, but we do have to solve for the spring constant. So we have this equation right here, which means K equals mg over L. It's 3 kilograms. Gravity is 9.8. L is 392 millimeters. This comes out to an even 75, which is nice. We also calculate our omega naught, the resonant frequency, square root of K over M. So we just got K, 75. We know the mass is 3. We know that this is 5. Finally, one more thing. We have to figure out gamma. We have the damping force is 45 newtons when the velocity is 50 centimeters per second. So we set up that equation from before. F of d is gamma times x prime. So when we plug what we know, 45 equals gamma times 0.05, or 0.5, because it's 50 centimeters per second. We get that gamma is 90. So with all that set up, we can find our equation now. So we have our equation 3x double prime plus 90 from gamma, 90 x prime plus 75 from k. 75 x equals our external force 10 cosine 5 t. That 5 comes from our omega naught that we also calculated. So let's solve this just how we solve any other non-homogeneous constant coefficient equation, we start with the complementary solution where we have to get our roots, right? So in this case, what we get is, first of all, we get a polynomial, right? 3r squared plus 90, r plus 75. So when we're plugging in our roots, we do negative 90 plus or minus square root of 90 squared, negative 90 squared, or sorry, just 90 squared, minus 4 times 3 times 75. This is just quadratic formula all over 2a. What this comes out to, I'm just going to tell you guys, it is negative 15 plus or minus 10 square root 2. So what that means is that our complementary solution, these are two real roots, even though they're not like nice numbers, they still work just as well in our solution. So R1, R2, they're different, plus or minus, so we just plug them into that same form we've been using over and over again. So now, like I said, this function follows a periodic form, so we can use those shorthand notations and get the final answer, but you can also just use variation of parameters to get the same exact thing. So let's set up variation of parameters, knowing that this is our g of x. So since our g of x equals 10 cosine 5t, that means our guess for this solution is going to be of the form a cosine 5t plus b sine of 5t. So I'll write out the algebra on a separate board, but I will go through it rather quickly. X. That's t. So finally, we have our x t a cos t plus b sin of t. So we have our x prime of t, and this equals 5a 5a sine 5t plus 5b, minus 5b sine 5t, x double prime t is negative 25a cosine 5t minus 25b sine of 5t. Doing all of that, we plug it right back into our original equation. 3 times this last one, negative 25a cosine 5t minus 25b sine 5t plus 90 5a sine 5t minus 5b cosine 5t plus 75 a cosine 5t plus b sine 5t. You guys get it. And then we set that all equal to 10 cosine 5t. And I'm not going to do the math on that, but what I am going to say is it does work out to 450b cosine 5t minus 450a sine of 5t. And so what we know is that this has to equal our 10 cosine 5t. So like in that previous example, this has to be equal to 10. And this has to be equal to 0 because there is no sine component here. So we set this up. First of all, we know A is 0, and we know 450 B equals 10. That means B is 1 over 45, and we have our particular solution for this problem, which is 1 over 45 sine B sine of 5t. So finally, putting it all together, we have our complementary solution, which we just solved for. We have our particular solution. Let's write down the answer to the problem, and it is combination of both of these. And that is it. Any questions?
Yeah.
Yeah.
This is all of this work is just for one force equation.
Yeah, all of this work is for your all forces mass spring system.
Force and then.
Yeah, this is forced and damped. So yeah, you might get undamped, which we did an example of. You might get free, which is your homogeneous case, g of x equals 0. This is with all of them considered. That's the work you need to do for it.
So there's not an equation that would be not free and damped. No, I'm sorry.
No.
Free and damped.
This is no. Free refers to the external force, the F of t.
Right.
Damped refers to your gamma here. So depending on like the combination and how the question is set up, you might not have your external force, you might not have both of them, you might not have just the dampening.
Oh.
But so there's a combination of all four of those. But any other questions? All right, good luck.